Alrighty, so we are now on to AP Test Prep Level 3A. Okay, now this is going to be a very it seems like a lot, but this is just one little section in Chapter 3. Okay, this is intermolecular forces. Okay, intermolecular forces. Now, intermolecular forces are the attractions or repulsions enter between molecules. Okay, not within molecules, but between molecules. That's what the inter means. So intermolecular forces, or IMFs, they are the whole reason for why compounds and elements sort of act the way they do, pretty much, in real life. So macroscopically. The first one we're going to talk about is London dispersion forces. Okay. LDFs are in every, I cannot write today, in every molecule. Okay, it doesn't matter what it is, they got London dispersion forces. Okay, these forces, if you think about a basic atom, you've got your, we'll do different colors for it. You've got your negative outside and your positive inside. Okay, for both of these, they look like eyes. Okay, they're a good distance apart from each other, but when they start getting closer together, what's going to happen very quickly, might I add, is that the negative side of or the negative charge of one of these atoms on the outside is going to start to force away the negative charge on the other atom. Okay, this is momentarily. This is not permanent. All right. That's why these are very weak forces. We'll write that weak. And it's very sudden. So they start to force away some of the negative charge on one of the atoms. Then that exposes the positive center. And so what happens is you have something like this. Where the negative charge, we'll make sure everyone knows, this is the negative, this is the positive, okay? The negative charge is attracted to the nucleus of the other thing, now that it's temporarily exposed, and then the negative charge forced away over here, it is called an induced dipole, okay? And so this now has an induced dipole of a slightly positive end and a slightly negative end. So it's induced, it's not permanent, and eventually these are going to relax back into their regular states, and they may even go to the opposite side, okay? But this is very quick, this is very weak, and it is in every single molecule. London dispersion forces, okay? And I'm going to write out induced dipoles. All right, that's London dispersion forces. Next, we have dipole interactions. Okay, it sounds like it's exactly what it sounds like. Okay, dipole interactions, also known as like polar forces, are between two polar molecules. Okay, so water, water's a bad example. We'll do ammonia is a bad example too. We'll do HF. Okay, so HF is a polar molecule. Okay, there is a partial negative on the fluorine side and a partial positive on the hydrogen side. Okay, it is between two polar molecules, so another HF can come along and it will be attracted to the semi-positive side of another fluorine molecule. Or say one comes up here. Okay, so it's just between two polar molecules. I guess HF is a bad example too. Whatever, you understand what I mean. Okay, dipole interactions between two polar things. All right, I forgot one in between in strength. So I'm going in order of increasing strength of intermolecular forces. I forgot one that goes right here. And so in between LDF and dipole, and so that is going to go over here. Okay, so we're talking about here, this is dipole induced dipole interactions. Okay, and so it's a little bit different from LDF. So say we have a polar molecule here. It has a negative side and a positive side to it. Okay, as it travels along to a nonpolar molecule, make sure we have our nucleus here. As it travels along, it does the same thing as an LDF, except stronger. So the negative side forces away the electrons of the nonpolar one. Okay, forces them away. And now they have an exposed nucleus, which is positive. And so now there's an induced dipole of slightly positive to slightly negative. Those are deltas, not eighths. Okay. And now there is an attraction or an intermolecular force in between the two. Okay. So that's what a dipole, induced dipole interaction would be. Then you have dipole interactions, so interactions between two dipoles or two polar things. Nextly, we have put it dipole. It doesn't roll off the tongue like this. We're going to do ion dipole. Yeah, this one's self-explanatory too. So say you have an ion of sodium plus, okay, a full plus charge, and it's coming up towards water, let's say. Okay, water has a slightly negative and a slightly positive. Okay, it's got a dipole going up like that. So these are going to interact, the negative side towards the positive ion, and that is going to form, I drew it towards the wrong part. It's going to go towards the oxygen. That is an ion dipole, and it's stronger than a dipole. Okay, it's an interaction between an ion, a fully charged thing, and a dipole, which is two partial charges. Okay, and let's see. The last one we're going to talk about, the strongest intermolecular force, is hydrogen bonding. Now, this is not a real type of bond. This is not a bond. Okay, this is still an intermolecular force. However, it requires a hydrogen and three different things to form this compound. Okay, form this interaction. Hydrogen bonding requires the interaction between two electronegative elements. Okay, this includes N, O, and F. Okay, nitrogen, oxygen, and fluorine, and a hydrogen bridge between them. Okay, so two electronegative elements, okay, N, O, and F. It can be any one of those, but it has to be N, O, and F. The way I remember that is that we'll write this first, strongest, okay. The way I remember that is hydrogen bonding is not an ordinary formation. Okay, so nitrogen, oxygen, fluorine. Hydrogen bonding is not an ordinary formation. Okay, now between these two compounds that are hydrogen bonding, they have to have an electronegative atom bound to a hydrogen, and the intermolecular force has to go to another highly electronegative atom. Okay, it could be O, it could be F, it could be N. Okay, same here, could be N, O, or F. But there has to be two highly electronegative atoms and a hydrogen bridge between them. Okay, that bridge is stronger on one side than it is the other because of this bond, but nevertheless, it's a hydrogen bridge. Okay, so those are the different types of bonding. Okay, there are some things that affect the strength of these bonds. Okay, in London dispersion forces, the things that affect it are the surface area, okay, so a interaction between this compound with multiple nucleuses and multiple electron bases. So the interaction between these two would be stronger than the interaction between these two, okay? They have more surface area of electrons and nucleuses to work with, okay? So the surface area affects these intermolecular forces, okay? Surface area. Anything containing a dipole, the amount, also surface area as well, surface area, but as well as the amount of charge. Okay, if there is a greater dipole, then greater dipole, then the interaction is going to be stronger. Okay, same here. So we have surface area, strength of dipole. Okay, and that's strength of the dipole times 2 because you're working with 2 different dipoles now. This one is surface area again, surface area, strength of dipole, and strength of the ion. Okay, if the ion is more charged, instead of a +1, we have a +2, say, then the interaction is going to be stronger. Okay, and hydrogen bonding pertains to just hydrogen bonding. Okay, it's sort of its own thing. But those are the intermolecular forces that we need to know of. Okay, if you have any questions, comment or email me, please. Stay healthy and good luck studying.